Hello and welcome to the shortest video in this entire course, 12.5 Vector Valued Function Arc Length. So, there's a lot of information in section 12.5. The only thing you're responsible for is the arc length of vector valued functions. The title also has curvature in it. There's all kinds of things. We're only doing arc length. Okay, so a little bit of a recap of the arc length formulas we already have. So for just a rectangular function, a y equals f of x function, remember the arc length was the integral from x equals a to x equals b of the square root of 1 plus the square of the derivative of f of x dx. That was in section 7.4. In section 10.3, we did parametric arc length. So now we had x equals f of t and y equals g of t. So the arc length was the integral from t1 to t2 of the square root of dx dt squared plus dy dt squared, or of course you could call dx dt f prime of t and dy dt is g prime of t. In 10.5 we did polar arc length, where r is a function of theta, and that's the integral from theta equals alpha to theta equals beta of the square root of r squared plus dr d theta all squared d theta. Now, in this section, 12.5, we're going to go to vector valued function arc length. Now, if you think about it, really a vector valued function is r of t equals f of ti plus g of tj. You could also think of it as x of ti plus y of tj, but let's stick with this one. So really, remember when we graph it, it's really a set of parametric equations. So if you go back to our parametric equation formula, which is this formula right here, there it is again. It's really just the exact same formula. Now there's one little trick to this, and this is the other way of writing it, dx dt, dy dt, or this is the other way of writing it. But if you look at this expression, the square root of something squared plus something squared, hopefully that would make you think of magnitude. And it would be the magnitude of the vector r prime of t, because remember it's usually the square of the x component plus the square of the y component. And the x component here, you have the derivative of it. So if r of t is x of ti plus y of tj, r prime of t is x prime of ti plus y prime of tj. So it just happens that this is the magnitude of the derivative of the vector valued function r of t. And again, here it'll be from t equals some value to another value. And these will be real numbers. Okay, so this is me explaining that whole thing as to why that's equal to that. The only problems in 12.5 that you're responsible for are numbers 1 through 6. So we're going to do one of them. And the question is to ask you to sketch the plane curve and, more importantly, find its length over the given interval. Now, they just say over the given interval, and they give you an interval. Would have been nice if they'd have told you that that interval is a t interval, not an x interval, or a y interval for that matter. Okay, so here's the first example, number 6. You have r of t equals a times cosine of ti plus a times sine of tj. Okay, why they couldn't pick a number, we don't know. So a is some unknown constant. Now, you know in the formula we're going to need r prime of t. I'm going to go the root of the magnitude of r prime of t. So r prime of t, of course, that'll be derivative of cosine is negative sine, and you've got this constant a, derivative of sine is cosine. So the original function r of t, let me actually join that up with green. Do I get choices of color maybe? Well, I don't know what color this is going to be. Oh, look, it's blue. Okay. Oh, it's because I have that highlighted maybe. Okay, we have a problem. So, anyways. So x equals a times cosine t, and the y equals the a times the sine t. That's turning it in kind of to a parametric equation. So if they ask you to graph it, so we're going to eliminate t. So you know the drill. We're going to isolate cosine, isolate sine, square both sides, add sine squared plus cos squared. We're going to get 1. On the left, you'll have this expression here. Multiply both sides by a squared. You find out it's a circle, center origin, radius a. And as far as the direction, you would do this right here. Let t go from 0 to pi over 2. It'll go from the point A0 to the point 0a. So, okay. Now, it's asking you for the arc length. Well, the arc length in this case, really, oh, I forgot to give you, let me look at that actual example. Number 6 is 0 to 2 pi. Oops, back over here. So, in our case, and I should write this down, 0 to 2 pi. Whoops, sorry about that. I have no idea why it just did that. 2. Oh my, it's not behaving well at all, is it? Okay, that's a 2. It doesn't like me to write that. Oh my goodness me. Okay, I will take that off, and actually I'll keep that, and that's a 2. Just trust me on this one. So, in effect, they're asking you to go from, 0 to 2 pi. Obviously, I'm looking at the wrong one. Number 6. I must be doing something like number 6. So I guess forget all that, because for some reason, I'm going from t equals 0 to t equals 4, and I don't know why I'm doing that. I don't know why that is there. But if we're going from 0 to 2 pi, that means we're going from here all the way around, which is basically the circumference of the circle, which is 2 pi r, and the radius of our circle is a, and therefore 2 pi is 6.28a. Okay, but if you didn't notice that, you would go 0 to 2 pi, and you do the standard. Actually, I didn't do the derivative here. I could have, but I didn't, so I don't know why I found that. Oh, I did. So I took the derivative of x prime of t and the derivative of y prime of t and the square root of, squared them both. You get the following. You pull out the a squared. The square root of a squared is a. And sine squared plus cos squared is, of course, 1. Square root of 1 is 1. When you integrate 1 dt, you get t. You evaluate from 0 to 2 pi. You replace the t by 2 pi by 0, subtract. All that work, you could have just done the circumference.